Yeah, welcome back, and thanks to the organizer. Really, I think it's been a great conference so far. And so I will be talking about ExpAn, the library we've been working on for the analysis of A/B testing. And I think many of you have already heard about A/B testing. Some of you have implemented your own versions of version A, version B of your website. Probably even used either some existing tools or have written your own analysis code to evaluate which version performed better. So you might be wondering why. So are we reinventing the wheel here? Actually, Rennie Schrupp, which is the ex-director of engineering at Google and now at Stitchfix, I think, asked himself almost more or less the same question. So what he said is basically almost each company at some stage has implemented one of the following systems, be it a logging system, message queue, ETL routines, job scheduler. I think you can add arbitrarily many items to that list. And one of that is, of course, A/B testing. Oops. So the answer he gave to this question, whether we should reinvent the wheel or not, is yes and no. On the one hand, people can argue that you always have different use cases, that each company in different industries has to implement their own somehow in-house solutions. But so this argues for yes. On the other hand, it's always often the case that people underestimate the effort of coming up with a certain generic solution. So basically, to implement A/B testing framework analysis library is not that complicated, but to come up with a statistically solid generic solution actually takes some effort. So that's why I'm here today. And before diving into A/B testing, I want to say a few words about myself and how I end up as a data scientist at Zalando. So I'm a systems biologist by education. What that means is, if that term is new to some of you, what we do is first come up with some mathematical model to describe a certain biological process or system. We simulate that model in the computer by varying certain parameters. Then you can go back to the lab and check whether you can reproduce the model behavior in a petri dish under some microscope. So you can either confirm your mathematical model, which means that you are a step closer to understanding the biological system. Or the experiment could actually tell you that your model is wrong. Then you go back to modify your model and start over the whole process again. If you think about it, this is probably always true for any kind of empirical scientific discipline, which is also somehow similar for A/B testing. So what happens here is you have some hypothesis in mind. You perform some experiment by randomly assigning users to different groups with different treatment. After gathering, so the randomization here is crucial. So basically, it ensures that the effect you are measuring comes purely from the treatment itself, but it's not affected by any other kind of confounding variables. After gathering some data, you can perform certain analysis and basically evaluate either version A or version B performed better. And you start with a new hypothesis again in this cycle. So A/B testing is not only very close to a scientific discipline, It is also quite widely adopted in companies that in different industries, right? So I think the reason is that is twofold. So first of all, more and more people are advocating for like data-driven, data-first culture in the company. If you think about the data-driven decision making, so the first thing that come up to your mind is probably A/B testing. So on the other hand, it's also a very serious business that we are talking about here. So from Obama election campaigns to certain online shop optimizing user experience on the website. So you have various examples of where A/B testing has really brought value to the company. So value being either monetary values or in the case of Obama election campaign, so in which case the A/B testing has brought more voters supporting the candidate, or some e-commerce website can use A/B testing to gain much higher user engagement and user retention. So how does ExpAn fit in this landscape here? So ExpAn is exactly this magnifying glass here. By the way, it stands for experiment analysis. What it offers is analysis of A/B testing or ABCD testing, so with multiple variants. And not only handles binomial variables, like typically interesting in the online world, like a conversion, click-through rate. Also deals with multiple other kinds of metrics. It's open source, it's written in Python, so that's reason enough that you should start using that. What ExpAn is not, we didn't include in the library, so to say, random number generation process, the random splitting process to perform the experiment, which we think is probably a special field that needs fine-tuning to adapt to the different use cases in different companies. What is also not in the library is the data fetching part, which we think is too domain specific. So I would be quickly going through the three main components of the library. So first of all, the experiment object, which is composed of different data sets. And then I will be talking about the core of the library, like the analysis functionality, which is actually the number crunching part. Finally, I will present you the, so to say, results structure that is very generic and can incorporate all the different kinds of analysis. First of all, you can usually describe your experiment with a bunch of attributes. For example, the name of the experiment, names of the data sources. What is important here is the baseline variant, which is also the control group that you want to compare to. Also interesting is the so-called primary metric, so sometimes often called overall evaluation criteria. So it's basically the metric that the experiment or the analyst should be focusing on, and also for example, the sample size estimation should be based on that one. Then we have so-called key performance indicators. So this is some metric that we measure in different variants, which is actually caused by the experiment. Right, so for example, we can measure for a certain customer what's the buying behavior after he's exposed to some treatment. And this can be usually represented in such a table format. So you can defined for each entity, which is also the experiment unit. Often case is customer. So for each entity which belongs to a certain variant, can define multiple arbitrarily many number of KPIs. It can be also time resolved, meaning that you can measure basically the KPI at different time points. I'll be talking about that, why that's interesting in a minute. So in addition, we have the so-called customer features. And that's also some property of a user or customer, but it's measured prior to the experiment, right? So typical features, what you can think of is age, gender, previous behavior of the user. Because, again, it's measured before the experiment, so it's never affected by the treatment itself. Similarly, you can define for each entity from a variant a bunch of features. In this case, it's usually not time resolved. Based on that, it's already quite easy to load the data into ExpAn and start the analysis. So the first thing you have to do is, what usually happens is you fetch the KPI and feature data from your customize your favorite database. You put it into some standard data format, either CSV, HD5, I don't know what. This can then be easily loaded in Python, and afterwards, what you do is you need to create a so-called experiment object. What is important here is you have to again define the KPI, the feature data, the metadata, and also the baseline variant. So as I talked about before, you can measure like more than 2 variants in a single experiment, but in this case, it's always crucial to define a baseline variant, so the control group that you want to make your comparison to. So after that, it basically says that the experiment with this name, it has this many features, this many KPIs with a primary KPI called normal shifted, has this many sample size, number of variants, here A being the baseline variant. So now can already start the analysis. So that's also the more interesting part. So first function you can do is what we call it delta. It's basically measuring the difference between different variants. So imagine that you sampled these 2 distributions from 2 variants in your experiment, and you are asking yourself, okay, whether the means of these distributions differ, right? Whether the difference, whether they are statistically different. So, and this is what this delta function does. Not only comes up with some point estimate of this delta, so the difference between 2 means, also calculate this confidence intervals based on either assumption of the normal distribution, or you can use non-parametric bootstrapping to calculate the confidence intervals. So typically you can measure the delta in different KPIs, KPI 1 and 2 in your experiment, and what you have to judge is so whether this confidence interval based on certain confidence level include 0 line, right? So it's if in the case of delta KPI 1, so it's statistically significant, different from 0, which means that this two variants performed differently based on this KPI, but on the other hand, there's probably no change if you are calculating the data KPI too. The next interesting function is also where you can make use of the time-resolved data is what we call the trend analysis. It's basically the same data analysis over time. So again, yeah, you can follow the trajectory of the difference between variance over time, also the confidence intervals. This is especially interesting. Has at least two use cases. So first of all, it's interesting to observe certain kind of seasonal behavior based on that, right? So it's a weekly pattern or a daily or even hourly pattern. And the second use case is it's useful to plot trend and differentiate between short-term and long-term behavior. So it's often the case that so sometimes a treatment, so experiment is different from experiment. So sometimes a treatment actually has very transient, like short-term effect, in which case the user reacted to that quite positively in a very short time period, but after a while the effect kind of saturates and the effect just diminishes. Alternatively, can be the case that in the beginning, the treatment effect is simply slowly ramping up, and you cannot, for example, it's only affecting the long-term like customer satisfaction. So you cannot observe or measure anything in a very short time period, but in the long run, you can measure a different impact. So that's why that's how this analysis comes into the play. The next one is what we call it subgroup analysis. So the name comes from actually medical literature, so clinical trials. What people are interested here is not only the overall estimation of impact of the treatment, but rather some differential treatment effect. Meaning that I'm measuring the same data KPI again in this case, but not anymore for the my whole like user group in the experiment, but rather divide them into subgroups based on certain features. So in this case, we have a feature which has two categories. Could be something like whether this user is a Python programmer or not. So if yes, he reacts positively to treatment. If no, we don't observe any effect, right? So of course, there's if you are drilling down diving deep into the data, and there's a multiple comparison problem that you have to take into account and correct for that. So then we come to the results part. Similar to the input metadata, we can also define some result metadata. So most of the attributes are inherited from the input metadata. Name of the experiment, baseline variant, primary metric, and so on. What we actually also persist in the result metadata is, for example, the version of the library that was used in the analysis, and the error, the warning messages, which happened during the analysis. So the actual data, result data, can also be put in this kind of table. At first sight, it looks quite crowded or involved. I'll just try to walk you through what each of these means, and I want to convince you that this is really a generic structure that can incorporate different kinds of analysis. So for example, for a metric called KPI1, we define a bunch of so-called statistics for different variants. This is the case, so you can summarize results for the data KPI with this structure, right? Optionally, if you are running the subgroup analysis and the over time, the trend analysis, you can also add three additional indices to depict the name of the feature that you are looking at and the name of the subgroup, right? So simply means for KPI1, what's the impact of people of the age between 20 and 30. You can also specify multiple time points. And so the first interesting statistic is so-called uplift. This is basically the delta, so the difference between the variant you are interested in, the baseline variant. So baseline variant here being A, and so the uplift of variant A compared to A itself is of course 0, and which is something we are not interested in. And this is the actual delta we are measuring. Sample size for different variants, of course, and here we call it uplift percentile. This is where we capture the so-called confidence intervals, where we define, in this case, the 95% confidence intervals. So it's based on the 2.5% percentile and 97.5 percentile of the distribution. Again, we are looking at these two numbers, which defines the error margin of your point estimate of the delta, and finally you have the absolute variant mean for these two groups, which is also interesting to calculate the relative uplift or the relative change from different variants. And so that's pretty much it. So what I've told you is we've recently published our code on GitHub and also Python package index. I introduced you to, so to say, standard input-output format that we came up with. The library also includes a battery of statistical analysis functions. It's because the library is designed as a standalone component. I have to say, as we also have experience that the library is can be really easily used either by some data scientist, or by some kind of microservice which implements the A/B testing framework and then calls the library to perform the analysis. We included the parametric statistics for confidence interval calculations, and also non-parametric bootstrapping stuffs. Of course, this is an open source project, and you are all part of the community, and you're able to shape the future direction, so to say. But at least two very natural next steps will be, we want to include certain visualization functionality. So this is essentially to make the library more user-friendly. Pictures worth 1,000 words. So you can, if you can easily visualize the results coming out from an experiment, it just makes the analysis more fun. And if you've been to Nora's talk this morning, and you already realized how Bayesian statistics is important, this is especially powerful if you so. Basically, you can not only look at means of different distributions, but look at the whole posterior. And also interesting in the use case that you want to continuously monitor the experiment, so that you don't want to run into this multiple hypothesis testing problem. All right, I'm just looking at the time, which is pretty good. Just want to thank. So these are the contributors so far, and of course, hopefully you will be the next. Simply reach out and make the community grow, and thanks. I'm happy to take questions.
For the nice talk. Are there any questions? I'm sure you have questions.
Yes. So what's the focus? So question is, what's the focus? How important is performing more, providing more functionality versus optimizing the performance, right? So the question, how whether it is possible to work with the library on a large data set. Currently, our experience is, we don't really work with large big data. Of course, Zalando is a big online shop platform, but in the end, usually the data we are dealing with can be easily fit into a single machine. Yeah, of course, the data cleaning part in the beginning is it can be some distributed database, right? So but after you fetched this data, you've aggregated them somehow in this standard format, and when you are running the analysis itself, when you are loading it into ExpAn, it's usually small data. So, yeah, that's the experience.
More questions? Okay, then let's thank Jie again.
Thank you.